DeepViz. Explaining long short-term memory network with high-dimensional time series data. Neural networks are applied in numerous fields, including stock prediction, self-driving cars, handwriting recognition, medical image analysis. However, the deep neural network is still a black box, leading to difficulty in explaining why a model works or fails. In this work, we introduce a way to open the black box with long short-term memory network. Here is a typical structure of an LSTM artificial neural network. We will explore what happens to the network components and try to depict and explain the mathematical model of neural net. On the left is the structure of an input or intermediate node, in which instances are listed vertically and cell colors encode the temporal values of the series. On the right is an output node, instances are listed horizontally and values of these instances are listed vertically. We reorder the data entries based on their output values for visualization purpose. This order is used for visualizing input and intermediate nodes in LSTM layer and dense layer as well. The ordering of instances is for visualization and does not impact learning process. This ordering is intended to help people recognize some of the patterns included in the result. The next section will cover the use cases on real-world datasets. Demonstration. Here is the interface of DeepViz. For model configuration, user can modify the hyperparameters of the model, such as epoch, batch, and learning rate. Weights can be filtered for a clearer visualization and to see the main contribution to the network. Training and testing loss are visualized with mean square error measurement and can be traced back to see history of training with evolution of weights. For a typical model of LSTM network, input gate, forget gate, cell state and output gate are specified. In terms of architecture, the hidden layers can be added or removed. Users can select input data from load model button with input data from high performance computer center, SP500 stock data, or US employment data. Then click start to start training. Here is a snapshot of fast forward training process for high performance computer center. The dataset contains 10 variables, which are computer health readings for every 5-minute interval within 5 hours, including CPU temperature, CPU load, memory usage, power consumption and fan speeds. Our target variable for this data is the CPU temperature. For this high-performance computer center dataset, as you can see from 3 first layers. The first layer is input, and there is no pattern. The second layer shows somewhat a pattern for input. The third layer presents more clearly the temporal dependency as we can observe a diagonal pattern. Moving on to SP500 stock data, here is a snapshot of fast-forward training process. Training and testing output are aligned gradually with the target, and the loss stops decreasing at around epoch 20. The dataset covers stock records for 5 weekdays each week, from 1980 to 2019. Each record contains the timestamp and stock price at open, high, low, close, and volume. We use stock price on Monday, Tuesday, Wednesday, and Thursday to predict close price for Friday. Let's trace back at epoch 10. The history of weights shows changes in this set of parameters. The originally thick lines decrease their width, the originally thin positive lines switch into negative and adjust to the larger magnitude. Meanwhile, back at epoch 3, the scatterplots for training MSE and testing MSE both contain a vertical shape of outputs. Because in the early stage, the parameters are not tuned properly and in ReLU function, negative input will result in zero output. Moving on to the US employment data, here is a snapshot of fast-forward training process. The US unemployment data comprise monthly for 50 states from 1999 to 2018. There are 15 variables in the collected data, including total non-farm, construction, manufacturing, education and health, and government. The target variable is the monthly unemployment rates of the states. We can see the contributions of significant variables to the output. The first node contributes with greatest positive contributions, opposite to the second node. While the other 2 nodes make marginal contribute as the observed links are really thin. These 2 last nodes do not demonstrate any clear patterns to learn. Thank you for watching.